way we see and move through the world depends on our body size. When you're swimming at the beach, the plankton floating next to you won't feel the water like you do, mainly because it's about 10,000 times smaller than you are. By watching waves constantly pounding on rocky shores, it's hard to think that such small creatures would be able to glue themselves onto these rocks and survive all those impacts. But that's because we're looking at the marine world through the lens of someone that's 10,000 times larger than these creatures are. This is what scientist Tom Hata wants to figure out. For his research, Tom measures water velocities in this very delicate area, the region less than the thickness of 2 pieces of paper above the surface.
How to make measurements in a precise manner is my challenge. Delicate instrumentation traditionally used for this purpose wouldn't be able to withstand the forces of breaking waves.
Tom had to invent and engineer his very own device.
I am by no means an expert in constructing things, but I'm always eager to learn new ways to build my own equipment.
The device itself is a small triangular block with several pressure points.
The velocity of water rushing over the sensor can be calculated by measuring the difference in pressure across the ports.
The device is bolted into the rocks during low tide, and the data is fed to a laptop via 300 feet of cable.
By measuring water velocities under a variety of physical conditions, we may be able to more accurately predict which kinds of organisms can settle where and how long they can survive. The triangle is so small that you can build like a fake mussel bed, you can build a fake rock formation around it, and then if you know, if you go out there and then you know where those things are in real life, you can understand what kind of flow patterns you expect from there, and then because you have an idea of what kind of flows there are, you can take a guess at what kinds of things can live there in the future, or how long these mussel beds are going to last, because they might get ripped up by the next big wave or something.
It doesn't stop there. Tom is also designing a way to recreate those high flow conditions in the laboratory setting.
Previous measurements along rocky shores have shown that the flow under breaking waves can routinely exceed 5 meters a second, or around 11 miles per hour. This is really fast, so it's actually hard to recreate this in lab settings. In steady flows, and even harder to recreate it when the flow has to go back and forth, like when you're under an oscillating breaking wave. So I've designed this device to help me recreate this in a lab setting. What this is a big hydraulic arm that can exert about 2 tons of force on anything that it's pushing down on, and it's pushing and pulling on this cylinder right here that pumps water in and out to these narrow jets in an aquarium. So I actually built this device using a lot of spare parts we had lying around the lab. Now there's a lot of different ways they could go about and build something that does the same thing, but I really wanted to just re-tinker the existing lab equipment and parts that we had on hand. You can be a scientist too. Tinker with my research challenges online in the Curiosity Machine. Stay curious.